Welcome, deeply curious minds and future aviators, to another thrilling deep dive. When you gaze up at an aircraft, effortlessly carving a path through the sky, it's easy to be mesmerized by the majestic wings or the sleek lines of the fuselage.
Mm.
But beneath that exterior, within the heart of its roaring engines, lies a system of immense controlled power, one that often goes unseen but is absolutely critical to flight: the gas turbine exhaust system.
That's right.
Today, we're not just glancing at it, we're plunging into the fascinating world of how these systems work, why they're designed with such, precision, and the relentless engineering challenge of noise suppression. This isn't just a conduit, it's a powerhouse of engineering that profoundly impacts engine performance, safety, and even our environment.
Indeed. And for those of you meticulously preparing for your ATPL theory exams, consider this session your essential strategic briefing.
Yeah.
Our mission today is really to dissect these complex concepts.
Yeah.
We want to highlight the specific knowledge points that are not only likely to appear on your test, but maybe more importantly, will solidify your foundational understanding.
Right.
We aim to spark those aha moments, the ones that transform rote memorization into genuine comprehension, equipping you to confidently tackle any question related to these vital topics. We've extracted the most crucial insights from our material, making sure you don't just know the answers, but deeply grasp the why behind them.
Absolutely. So let's begin by shining a light on what we often call the engine's unsung hero, the jet pipe. Now, at first glance, it might seem like a pretty straightforward component, just a tube to guide hot gases out.
Right. Seems simple.
But that couldn't be further from the truth. The exhaust system, and particularly this jet pipe, is actually an incredibly underrated part of the whole propulsion unit. Its design, believe it or not, exerts a truly considerable, almost hidden influence on the overall performance and efficiency of the entire engine. It's sort of a masterclass in passive engineering.
What's truly fascinating here is precisely why it's so often underrated. It doesn't actively generate power like a compressor or a turbine, doing the obvious work.
Right. It's not spinning or burning fuel directly.
Exactly. Yet its passive role is incredibly active in optimizing the entire engine's operation. For a pure turbojet engine, for instance, the exhaust system isn't merely about expelling gases.
No.
It's about ensuring those superheated gases exit in precisely the correct direction and at the optimum velocity to generate the engine's primary thrust. Get that design wrong, maybe a kink, an obstruction, or even just an incorrect taper, and you lose precious efficiency.
And that directly translates into less power, more fuel burn.
Absolutely. It's about harnessing every single bit of kinetic energy for propulsion. You can't afford to waste it.
And the dynamic shifts quite dramatically for turboprop engines, doesn't it? We understand that for turboprops, the design of that outlet nozzle isn't primarily about maximizing jet thrust in the same way.
That's right, the focus changes.
Instead, it largely dictates critical factors like the turbine gas temperature and, crucially, the back pressure at the turbine itself. So while it's still about managing exhaust, its specific engineering role pivots. It highlights how critical context is in aviation design. It's definitely not a one-size-fits-all solution.
That's a crucial distinction, and one you'll want to remember for your exams. The performance characteristics of a turboprop are highly sensitive to the conditions immediately after the turbine.
Okay.
If the exhaust system doesn't manage back pressure effectively, it can actually hinder the turbine's ability to extract power to drive the propeller,
Which means less efficiency.
potentially leading to increased fuel consumption or even reduced engine life over time. This leads us right into considering the extreme operating conditions these systems have to endure. The gases entering the exhaust system are typically between, say, 550 degrees C and 850 degrees C.
Wow.
Now, that range alone is incredibly hot. We're talking temperatures that demand specialized high-temperature alloys, various stainless steels, nickel-based superalloys, and very careful thermal management.
And 850 degrees C is already enough to melt aluminum. Steel glows cherry red at those temperatures. But here's where it gets really interesting, especially for your ATPL exams. If afterburn...
All right. Many thanks for listening to this free part of the ATPL Theory podcast. If you want to continue learning and access the full comprehensive guide, go to my Patreon at patreon.com/ATPLtheory or my Hero at herohero.co/ATPL. That is patreon.com/ATPLtheory or herohero.co/ATPL. Wishing you all the best.